Good afternoon, everyone. As Jeff said, I'm Justin King with AMD. This is Arun. He's with Google, and we are the co-chairs of the UALink Consortium Systems and Manageability Workgroup, here to talk about management and control of UALink scale-up pods. Go to the next slide. Oh, we have control, don't we? All right, excellent. So UALink is a scale-up fabric implementing load, store, and atomic operations between accelerators and enabling access to memory on those accelerators. UALink is focused on low latency and high bandwidth. The first UALink base specification to come out was the UALink 200 specification. It leverages Ethernet, specifically 802.3DJ. For its physical layer, that means we can reuse things like Ethernet cables, Ethernet retimers, but it defines its own data link layer, and as well as transport and protocol layers above that physical layer. That lets us simplify things, slim them down, and really focus on the important parts of a scale-up fabric. When we're talking about UALink, and especially managing UALink, a critical piece to understand is a UALink pod. We heard about pods earlier, but in our definition, a pod consists of a collection of system nodes with host CPUs and accelerators, as well as switch platforms to do switching, connect those accelerators together, and get them to talk. UALink is currently restricted to 1024 accelerators. We think that's a pretty healthy number for scale up at this point in the industry. But 1024 is simply a maximum. We encourage a wide variety of system designs for all sorts of applications. Now, the unit of management may be a UALink pod, but I went the wrong direction. But the unit of tenancy, what can be assigned out to a particular tenant within a pod, is what we call a virtual pod. It's the unit of isolation of a workload and of workload scheduling. So in order to actually run a workload, you need to create a virtual pod, but your pod can be partitioned into multiple virtual pods. On the simplest case, your pod is simply also the virtual pod. They're directly overlapping. Virtual pods can be created to support multiple tenants within a single physical pod. For example, running multiple models for inferencing at the same time. And they are isolated from each other by using route entries in the physical switch.
Thanks, Justin. So routes, that's where the management aspect comes in, and we have chosen a centralized control and management architecture here, called SDN. So there is a pod controller that sits outside the boundary of both the switch platform and the system platform or node platform as such. There are agents on each of those. There is an SMA as a switch management agent. Then NMA on the node management as the node management agent. We are focused on defining the interfaces between the agents and the pod controller, as well as the interfaces southbound of the agents towards the switch ASIC, and a little less towards the GPU right now. But eventually we'll get there as well. We're not defining what the implementation of the pod controller needs to look like. That's where a lot of proprietary innovative values come in. From the switch management side, we are focused on trying to unify both the management and control plane. Like I said, we do have a control plane because we have to download routes. It's like it's very close to what the SDN architectures look like. And that unification comes through GNMI as the common protocol and RPC mechanism, and Yang as the data model. The data model is shared across both control and management planes. And then on the other aspect of it, the chassis management is completely out of UALink scope. that remains what is there today, both on the switch and on the accelerator side. And typically it tends to be Redfish, BMC, and that ecosystem. Kind of touched on this already. A UALink pod controller manages the entire pod, and then a node management agent typically manages multiple accelerators. So that's one system or one tray. If you think of it as a physical entity, we expect to see one node management agent, although we're not limiting it to that. You can have a tray that's bifurcated in any which way you want up to the implementation. We look at one NMA as one system node. That's our definition in a logical sense that also maps to a full set of accelerators that aligns along the physical boundaries now. And then we have Redfish. The NMA interface is Redfish. We're leaving that intact because of, again, how things have evolved or standardized on the server side. So the NMA can run on the BMC, or you can have your own control CPU there if you want to. We don't define that. We only define what the agent needs to do and what its interface is northbound towards the pod controller. As I said earlier, the NMA may also export telemetry and config also towards an actual chassis management plane, if necessary. We have stayed away from that. That's not UALink's role. The NMA's role from a UALink perspective and standardization is purely what we want to touch on the node side with respect to managing the UALink ports and related state on the accelerators. UALink switch platform, complementary to what we just went through. The main difference here is, of course, there's an SMA, but there is the interface is now GNMI with Yang modeling. We have defined our own Yang models. We've pulled some from OpenConfig with respect to types and basic Yang constructs, but otherwise we have defined our own Yang model. It's available on GitHub. All UALink members have access to that. We definitely want feedback on this. It is evolving, so we definitely want feedback on this. On the southbound side, we have defined UALink SAI. Justin will talk through it in more detail. So what does the pod controller manage? On the switch side, it manages top-down, carving out vPods, setting up switch ports, its state, modes, in terms of speed, if there's additional fault management policies to set up those bits. And then switch ports are typically assigned to vPods. That's how we define a vPod towards the SMA itself. And then the topology management aspect, neighbors can either be purely discovered or they can be configured and verified. We offer both options. And then routes. Routes are where the segmentation aspects come in. A vPod is strictly confined by defining routes correctly, and the routes are authoritatively synthesized by the pod controller and pushed down. The SMA, and also on the other side, if routes end up on the NMA in the future, they do not, strictly do not have the authority to create their own routes. That breaks the security aspect of segmentation. And like we talked about, UALink has already adopted GNMI as the transport and RPC, and then Yang modeling.
So sitting below the switch management agent, the SMA, is the UALink switch abstraction interface. We heard in the UEC talk earlier about their extensions to the OCP switch abstraction interface. When we went and took a look at this, we realized that a gigantic piece of that OCP switch abstraction interface did not really apply to us because we do not have a Ethernet data link layer and above. And so we have taken the approach of developing our own switch abstraction interface. For those who are UALink Consortium members, we have a copy of this in our private GitHub, but it's intended to have a very, very similar approach to the OCP SAI, but a different code base. We do intend to have easy integration with things like Sonic, if that's an interesting option for a switch management agent for you, but there's no restriction that you're limited to SONiC only. This is a set of C APIs, at least in the 1.0 spec. That's how we're restricting it. And this enables multiple different switch vendors to provide their own runtimes as well as their own hardware and device firmware, while enabling a unified approach to management up at the switch management agent. UALink Consortium does not currently define any sort of physical interface or any protocol stack to communicate with the switch. That is all vendor defined. Did we talk about this?
I can take this. So
We did that slide already. Yep. Okay. So putting all of this together. This is a picture with a lot of details on it, but we're showing down at the bottom the 3 system nodes that each hold 4 accelerators as well as a host CPU. Up sort of in the middle, we have a set of 3 switch platforms, each hosting a switching ASIC. The system nodes have a node management agent. The switch platforms have a switch management agent, and all of those are connected together to the UALink Pod controller that centralizes management and control.
Yeah, sorry, we made you squint on that. Some user journeys listed here. Again, definitely looking for feedback, especially from the scaled out deployments that we expect to see from UALink. If you look at the infrastructure provider, a CSP, starting from the top, there is the physical pod topology management itself, starting from, port control, neighbor configs, and day 2 ops effectively, which is monitoring the topology for changes, allowing expansion, and those aspects. And then the pod controller does need to provide APIs towards the tenant or tenants for vPod creation. So that's the other aspect, a set of user journeys there. vPod creation, monitoring of the vPod and providing vPod capacity state towards the tenant so they can choose to either continue a workload, abort, or pick a different vPod up to the tenant. And then reporting of failures explicitly. Tenants may or may not be interested in this, but ideally for completeness, it's better that the pod controller exposes this. But again, the infrastructure provider is definitely interested in the vPod capacity tracking, so we know what's going on. How can we relate it to the physical? How can we relate workloads to physical failures like thermal failures or equivalent? And on the tenant side, it's just a complementary aspect of what we just talked about. vPod requests, creation, deletion, effectively the CRUD APIs or equivalents, and then we provide the capacity tracking towards the tenants. That these are all the APIs that the pod controller needs to support. And then call to action. We have all the links here. We do have GitHub. All the members of UALink have access to GitHub. We definitely want feedback on all the fronts we've talked about so far. Modeling, especially details around modeling. We're looking at push-based telemetry, streaming telemetry, and what types of frequencies and capabilities that you can support directly off the switches, off the GPUs. That's the other aspect. And then very happy to collaborate with all the other OCP work streams that have especially been discussed today to get a good amount of convergence especially between the switch platform and the node platforms. And questions?
So I have a couple of questions. By the way, Amit Pabulkar from NVIDIA. So do you see a world where the pod controller merges with the OpenRAC, the OpenRMC / infrastructure manager project that somebody talked about, right? You said in the last sentence that you would like to collaborate, compute, and network together. But do you see that people will actually deploy something in the same system, or will they remain separate? That's my first question.
We can.
So our philosophy in UALink management has been primarily to describe interfaces and not implementations. And so I could easily see a converged rack manager along with pod controller, but we are not defining any of that. We are simply defining the roles and responsibilities of the pod controller in terms of fabric management and what it must do downstream. Any of the other things like chassis management, those certainly could be complementary, but we're not touching on that. I could see that as a valid implementation choice.
Okay.
Yeah, and to add to that, pod controller can co-reside or be part of the OpenRMC implementation, purely up to the implementation, like what Justin described. If a pod is going to be multiple racks, that becomes difficult, so you're going to typically have it outside, right? So any of these options are on the table.
And the second question on the vPod itself, right? Like, do the tenants see the actual partitions that you're creating, or is that abstracted away? I mean, if I take a rack, right, and let's say you're hosting 2 tenants on it, do they know that they reside on the rack on a partition, or is it like abstracted away from them in some kind of a logical way?
Yeah, so a vPod is a logical construct. So we don't expose the physical topology yet, at least, but it's come up. As we look at INC, it's starting to become more evident. We may have to expose some of the topology constructs. But in 1.0, it's a purely logical construct. The tenants only see so many accelerators and how they're connected with respect to bandwidth, and that's really it.
I'm curious, has there been debate around not exposing the physical topology, or? Oh.
Yes, yeah. I mean, it is a security issue, right? So, so it's a debate in progress.
Okay, thanks.
Anyone else?
Any other questions?
All right, thank you very much.
Thanks, everyone.